Again, class. Okay, good morning. So, this is the second part of my presentation in gas turbine. So, I will present here an additional example class to the previous presentation. Okay? So, let us, class, consider here. In a Brayton cycle that operates between temperature limits of 300 Kelvin and 1773 Kelvin, with K equals to 1.4. Determine the temperature at the end of compression. Okay, isentropic for maximum work of the cycle. Take note, class. So, maximum work. So, therefore, since maximum work is uh, required, so we utilize. Okay, so as what I explained in the previous presentation, in the part 1 of this topic, so, for maximum work, T sub 2 is equals to square root of T sub 1 over T sub 3. Take note, class, that the problem presented here is in a multiple choice, okay, type, okay. So, we have option A, 700 Kelvin, B, 690.5, C, 730, D is 300 Kelvin, okay. So, as you see in class, in the option, the answer is letter C, 730. Okay? So, let us solve, okay, if this answer is correct, okay? So, for maximum work, T sub 2, the square root of 300 over 1773. So, take note, class, T sub 2 equals to 730 Kelvin. So, the problem is very easy, okay? So, I think if you solve, of course, alone to this type of problem, you can easily determine what is the temperature required. Okay. So next we have here another multiple choice problem. An ideal Brayton cycle has a network output of 150 kilojoules per kilogram and back work ratio of 0.4. Take note, class, that we have here back work ratio. Anyway, a back work ratio is the ratio of the compressor work and the turbine work. Okay, so take note of the term, class. Okay, if both the turbine and the compressor had an isentropic efficiency of 80%, take note. Okay, so we have also isentropic efficiency. Okay, so how this isentropic efficiency is applied to compressor and applied to a turbine or a gas turbine. Okay. So the network output of the cycle would be, okay, so A 59 kilojoules per kilogram, B is 98 kilojoules per kilogram, B is 75, D is 120 kilojoules per kilogram. Okay, take note, class, that the back work ratio is equals to compressor work over turbine work. So take note of this, class. Okay, take note of the ratio. Okay, so substituting values now. So the back work ratio is given, so 0.4 over, that is W, or the compressor work, over the turbine work. Okay, or getting the compressor work in terms of the turbine work, that is zero point 0.4. Okay, so only 40% of the turbine work is the compressor work. Okay, also work net is equals the turbine work minus compressor work. So we need this, class. So in order for our solution to be complete with an equation, okay? Because we have two unknowns here, okay? So getting now, again, substituting values, 150, the work net, equals to WT minus 0.4 WT. So the turbine work now is 250 kilojoules per kilogram. So without, class, applying the isentropic efficiency of the compressor and the gas turbine. So applying now, so for the turbine work, of course, if there is an inefficiency in the system, the work will reduce. Okay? So that is the term. But on a part or in a compressor part, the work will increase. Okay, take note of that class. Huh? In the turbine, the work will reduce, and in a compressor, it will increase because of the efficiency. So take note, in compressing the air, it requires more power because of the inefficiency. Okay? So getting now the turbine work, applying the isentropic efficiency, that is equals to 200 kilojoules per kilogram. Okay? And for the compressor work, 0.4 times 250 will become 100. Excuse me. Okay? So the actual work now is 100 over 80 is equals 125 kilojoules per kilogram. So the actual work now is equals to 75 kilojoules per kilogram. Thank you very much, class.